everything? Does it all become for granted with a wedding ring? Oh, there must be more. There must be another way. There must be conscious, different things in different ways. There must be love. There must be a reason, and a little bit of faith has got to come my way. I was just a little girl when my mama used to say, ooh, happiness requires work every day. Oh, and if that someone makes you smile and leaves you with a scar, don't let them tell you what you feel or who you are. Oh, there must be more. There must be another way. There must be conscious, different things in different ways. There must be love. There must be a reason, and a little bit of faith has got to come my way. I gave it all to you for too There must be another way. There must be conscious, different things in different ways. There must be more to the reason why we do it all for love. There must be more for a reason, and a little bit of faith has got to come my way. Has got to come my way. Has got to come my way. Do you ever feel you don't get out what you're putting in? All your hopes and efforts are all in vain. Who will pick you up when you've lost?
And welcome everybody. I'm so glad you're here for the live stream. I have been spending like a boatload of time in playing with OBS, Streamlabs OBS and scenes. And last night I did what an old man can rarely do, and that is I pulled an all-nighter. I was so excited about the themes and sitting. So that's what you experienced at the beginning of this live stream, was a few of those tweaks. There's more to come. I'm so excited about all of it. Okay, so our focus today is access control lists. And an access control list is a mechanism that we can use in a Cisco environment to match traffic. Now, that wasn't the way that I was taught about access control lists. The first thing I learned, like in the late 90s, when I started learning Cisco, was an access control list is used for filtering traffic. But that's just one of the things that an access control list can do. So what I'd like to do in this live stream and this recording is to talk with you about what an access list can do, and then the types of access lists, just a high-level overview, and then focus on a standard access list. And we're going to discover a few things about it that we maybe didn't already know. So that's our objective. So let's go ahead and take a look at the topology that we're going to work with, and then we'll put a plan together. So let's let's imagine that, so many great things we could work with here. Well, let's do this. Let's talk about what an access list can do first, and then we'll talk about applying it as for purpose in our network. So here we have a corporate network that's up here, and then we have this router and Metro Ethernet in Nevada and Florida. So let's use this as a little workspace over here, and let's talk about, in fact, let's talk about with the workspace right here, what an access control list can do. So an ACL, an acronym for an access control list. Maybe that's why people think right out of the gate that they are to control access. But an access list is really about matching. And if somebody asks us the question, well, what can they match on? That would depend on the type of access control list. Now, let's imagine that you and I have been hired to go and cover a party. So there's a party that's happening, and what we've been asked to do is we've been asked to go to the party and stand by the door, and we've been given a list. And here's how it works. We're given the list, and in that list, we have a list of people. Some of those people on the list are allowed, meaning we should let them in, and some people are not allowed, and so we should not let them in. So let's imagine that Bob, our favorite user Bob, comes by, and with Bob comes to the party, and we say, "Stop, Bob," and we say, "Let's take a look at this list." We look at the list, and if Bob is on the list, and it says, "Please allow Bob to come in," we will allow Bob to go ahead and come in. So Bob goes in, and now we have Lois, who shows up 5 minutes later. I don't know why they didn't drive together, but Lois shows up. So we say, "Hold on, Lois," and we take a look at our list. And when we're reading a list, where do you think we start as far as reading the list? On the bottom, on the right. Most of the time, if we have a list, we're gonna start from the top and go down, and that's how an access control list is processed as well. So when Lois shows up, we're gonna take a look at our list and say, "Who are you? You're Lois. Okay, great. 1 second. Now that we know who she is, we'll compare it against our list. We'll go down. Line 1, no match. Line 2, no match. Line 3, no match." And then if Lois is on that list, and we come to a line in that list that her name is on, we'll say, "Oh, Lois, great news, you match. But unfortunately, it says do not allow Lois in." I don't know, maybe Bob's having some kind of an extra something of... I can't play that game. Okay, so for whatever reason, on the list it says don't allow Lois in. So we say, "Sorry, Lois, you can't come in." It says explicitly on the list that we got to, you can't come in. So Lois goes away. We stop processing the list. So if there's 100 lines on the list, and we get to Lois at line 42, we stop. And we say, "Okay, great, we're permitting or denying her, and she's going to be denied." Then Manny comes along. Let's do Jill. So Jill comes along. So Jill comes up, and we say, "Wait, hold on a second, and let's check the list." And let's say there's 100 lines in this list, and we go through every one from the top to the bottom. Nope, doesn't match there, doesn't match there. Jill, nope, nope, nope. And then we say, "Jill, you don't match," meaning you're not on the list. So the question for you and I is, what do we do for Jill if she's not on the list? And if you're thinking, "Well, Keith, we're probably not going to let her in. She's not on the list." You're right. And that's really a lot like how an access control list matches regarding when it sees packets. It has a list. It goes through the list looking for a match. And if there's a match, it then takes that action. And there's only 2 types of actions with an access control list. And that is either permit, which means yes, or deny, thumbs down. And if you're not on the list, at the very end of that list is an implicit, fancy word for by default, it's the default behavior is deny. So a lot of times people say an access control list has a list of traffic or packets that we're trying to match on, and at the very bottom there is an implicit deny, meaning if you're not on the list, You're not going to match on the access list, and there's an implicit deny as a result. So that's what an access control list is all about. Now, in a world of IP, there's two types of access control lists for matching. Now, one is called a standard access list. And I better spell that correctly. That's our easy word. S-T-A-N-D-A-R-D. Great. So a standard access list is very, very limited. A standard access list can only match on the source IP information. Wait, what do you mean, Keith, the source IP? Well, we have that beautiful big protocol stack. So Bob and Lois, Lois didn't make it in the party, but Bob's in the party. He's using his computer and he's communicating. And as those requests are made at the application layer, like for HTTP services for web or DNS services to resolve names to IP addresses, and then that's handed down to the transport layer, and then TCP or UDP very likely is going to be used based on the protocol, and then it gets down to layer 3. And at layer 3 we have IP address information. And so a standard access list can only match on source IP address, meaning it doesn't have the ability on an access list, a standard access list, to consider anything else other than the source IP address information. So wait a sec, let's put that into context. You're saying that if we have a list, like you and I are the bodyguard, and we have Bob or Jill or Lois coming in, and they're all coming from their source IP addresses, that's the only thing we can match on in a standard access list, is the source IP address, where that packet is coming from or where they live, where they came from. Yep. It doesn't matter with the standard access. In fact, it's just not possible with the standard access list to match on. Is the layer 4 protocol TCP? Here's the answer. Let's do an interview with the standard access list. Let me get a hat. Here we go. So this is the standard access list. So this is the interviewer. Hey, dear Mr. Standard Access List, can you match based on the layer 4 protocol? And the standard access list says, with a too small headband, I don't know what that is. And then we ask the standard access list, can you match in your list based on the destination IP address? And the standard access list says, nope, don't know what that is either. All I do is I can only match on the source IP address information. That means, let me tell you what I can do. On a good day, says the standard access list, what I can match on is I can match on the full IP address, the source IP address, like Bob's IP address. Let's say it's 10.16.0.10. In this topology, maybe that's Bob's computer right there. So the standard access list says I can match on that exact IP address as a source IP address in the packet, or I can match on a range of IP addresses. But that's it. That's all it can do. It can only match on source IP information, and that makes a standard access list a double-edged sword, because it could be, it can't match on layer 4 protocols, it can't match on destination IP addresses, but it's pretty simple to create because it's only looking for the source IP. So it can't do a lot, but there are a lot of great applications for it. And if you happen to catch the live stream we did on NAT, Network Address Translation, we used the standard access list to control which source IP addresses would be candidates when packets came into a router for NAT. So a standard access list only filters on source IP address. That's it. Now, in contrast to that, what could the other type of access list do for us? And the other type is an extended access list. So an extended access list, it's not too nice to brag about things, but if we went to a party and we are using a standard access list and gave it to the bouncer or the people who are at the door, the standard access list, it would say, here's what I can match on. Are you ready? You got a minute? Says the extended access list as we take a look at what it can match on. It says I can do everything a standard access list can do, meaning I can match on the source IP address or a range of source IP addresses, no problem. And I can also match based on the destination IP address. So I can match on source or destination. So it's right out of the gate, it's like twice the ability of a standard access list. The extended can do both. And, says the extended access control list, I can also match on virtually anything at layer 4. So If you're looking for TCP at layer 4 or UDP at layer 4 or GRE at layer 4 or IPsec at layer 4 or anything else as a layer 4 protocol, it can match on that. And not to stop the bragging, Mr. Extended Access List, it can also match based on port numbers. So if we want to match based on TCP traffic from a certain IP address, going to a certain IP address, and going to or from a specific port, a TCP port or UDP port, it can match on that too. So we'll save all the grandeur of an extended ACL and how it works and demonstrating that for another live stream. In this live stream, we're going to focus on the standard ACL that just has the ability to focus and match on a source IP address. So, standard access list, we've now identified one of our goals is what it can match on. It can match on the source IP information. Now, once we have this access control list, we can do lots of different things with it. We could use it as part of our network address translation rules, which we did in the previous stream. We could use it to identify traffic for quality of service and mapping and marking of traffic, which we haven't covered yet in our live streams, but that's another use. And we can also use the access control list sort of like the bodyguard that we talked about, or you and I at the beginning of this discussion, standing at the door of the party and taking an access control list and then being told, enforce it and only allow traffic or people in that match that access control list. So what I thought would be fun is let's go ahead and create a scenario where we want to do filtering and stopping of certain types of traffic at a router. So we'll use router 1 as our device that we're going to create and implement an access control list, and then we'll tell that access control list or tell the router that on one of its interfaces it should go ahead and enforce that traffic rule. So let me show, oh, this is fantastic. So what this represents are all the IP addresses at the headquarters site here in Arizona. And basically all these IP addresses, they can be summarized into 10.16.0.0/21. Now, if that's beyond the scope of where you're currently at in your journey through CCNA, don't worry, because we're going to cover that in more detail as we take a look at the subnet Saturdays. And so if you're not quite ready for subnetting or summarizing of IP addresses, no worries. I'm just going to tell you right up that these addresses in Arizona, I saw Arizona, I freaked out. These addresses here in Arizona can all be summarized. They're all in this space of addresses of 10.16.0.0. And then all the addresses here in Florida are in another block of addresses. It doesn't really matter because we're not going to block these guys. I just want to block anybody who's coming from Arizona. So anybody who's coming from the headquarter location trying to go out, I want to go ahead and put a bodyguard right here on gig 00. And I want to tell that interface, gig 00, to only permit traffic that is specifically allowed to be permitted in the standard access control list that we are going to create and then apply to that interface. So that's our goal. We want to block anybody. So I got to tell you up front, though, Bob up at 10.16.0.10, he's not going to be too happy because he's not going to be able to get anywhere outside of his local Arizona networks. But I just want to demonstrate the function of the access control list. So let's do this. We have a couple options with a standard access control list. We can use a number, like, what do you mean, Keith, a number? Like a decimal number. So the numbers 1 through 99, traditionally, if we look in the history books for Cisco, that's their number that says, hey, these are standard access lists that can only filter based on source IP information. Then they came out with what was called a named access control list. And so we could either create a numbered access control list, 1 through 99, and put the rules in it, make the list, or we could do a named standard access control list. They both work. They both have the same effect. There's just two different ways of creating it. So what I think we'll do is our goal, and let me go ahead and bring my pen out. Our goal is going to deny 10.16.0.0/21, that whole network address range for Arizona, and we want to deny them inbound here on gig 00 on R1. So let's see. Are there any preferences? Let's do that. I would be happy to demo either way. We could do a numbered access list, or we could do a named standard access list, either way. So I'm going to go ahead and take a look at the queue. If you want to type in your preference, if you have one, or if you don't have one, say I don't have one, and I'll just do a quick check, and then we'll do whatever the majority of the votes I see want to do. So let's take a quick look and see what we think here. Okay, well, I see the first one in is a NACL. So in Cisco speak, a NACL would be an example of a named access control list. So we'll do that. And before we create that named access control list, let's make a plan. Let's call the access control list, because it's going to be named, let's call it sorry-AZ. And I'm going to be case careful there, because when we make this access control list, when we apply it, we have to do this right name. So I'm going to say sorry AZ, because we are going to deny all the traffic coming from this network statement. So, or from that network. So our first line needs to be to start off with, let's do our first line of deny, and I'll show you the full syntax in the interface. But for here, let's just write the logic. We'll say deny 10.16.0.0/21. And to do that, this is fun. To actually implement this, we're going to use wildcard bits. So if you've seen me in the, we've had the time together in the OSPF section with network statements and wildcard masks, these are similar to that, except they're called wildcard bits. And there's a reason for that, which I will reveal here shortly as well. So we're going to use wildcard bits to identify which bits we care about matching and which bits we don't. And then, this is really important, we also want to include, at the very end of this access list, we want to include a permit of everything else. And the way we spell everything else in the world of a standard ACL is any. And that's because when this access list is created and we apply it inbound on 00, if we just had one line and it said deny, that's it. Here's how it would read on router 1. Okay, here comes the packet. Standard access list. Deny this address. That's the whole list. Sorry, you're not on it. Implicit deny. That killed the packet. So if we want any traffic to be forwarded through that interface, once we apply the access control list, we have to have at least one permit statement somewhere. And if all we're trying to do is block that range of source IP addresses, we'd want to go ahead and apply the permit at the end. So we'll go ahead and do that. And there's the syntax for it. So without further ado, let's go to the interface. I need to take a moment and line this up. That'll be fun to do. So give me a moment. Let me hide that for a moment, and then let me line up the lab. And there it is. Hands-on practice is a great thing to go. If I remember today, I am going to share with you some details about packet panic. That's what the new name of my series is going to be, where it's going to involve 5 minutes of thinking and planning and 10 minutes on the clock to implement the solution to reinforce all the concepts that we've been talking about related to CCNA certification. It'd be a lot of fun. All right. I'd like to thank Jeff Kish for helping me come up with that name. It's a great name. Okay, so router 1. The first thing we're going to do on router 1 is verify that we're on the right device. So let's take a look at our topology just for a moment. So router 1, if we take a look at gig 00, and here's router 1. So it's gig 00 interface. Oh, it's not even labeled here. It's just showing the IP address. It should be a .5, 10.16.6.5 on that interface. I just want to make sure that we're on the right router. All right, so let me hide that away, and let's do a show IP interface brief, just like that. All right, and I see that address right there. So this is the interface that is facing upward. So gig 00 is the one that everybody in Arizona is going to have to go through to make it out of R1. We're going to block their entire address range based on our plan, which is right here, the 10.16.0. So the syntax to do that would be something like this. Measure twice, cut once, not a bad idea. If we do a show, IP, OSPF, I've got OSPF on the brain, show access list. One of the really nasty things that can happen is that if we don't know there's an access list already in place, and then we think we're creating one, but we're not really creating it, we're adding to it. It's like adding additional entries to the bottom, and it's a nightmare because we're going to have results that we didn't expect from that access control list. So I'm just doing this quick check just to make sure there's no access list currently on the system. And if there were, we could also check and see whether or not they were applied to R1's gig 00. But there's no access list here, so we're good to go. So let's do this. Config T, access list, question mark. Ooh, look at that. So we have the number right here. And this is how we would create a numbered access list. But it is not how we would create a named access list. So to create a named access list, we do IP access list, and then a question mark. And then we have the option for standard. So we'll type in standard and question mark, and then we'll give it a name. And I'm going to just take a peek at what we were going to call that. We were going to call it sorry-AZ right there. All right, sorry AZ. And we'll do that, SORRY-AZ space, a question mark, and boom, that puts us into named access configuration mode. So if we did a standard ACL with just the number, like 1 through 99, we just do the command, it would add a line, do the command again, it would add the line. But access list configuration mode, which we get with a named access control list, is actually pretty cool because it gives us sequence numbers. It'll actually do it for us. So the first entry will have a sequence number of 10, and next one will have a sequence number of 20. And the cool thing about having those numbers is that, oh, I forgot to put something in that access control list. And we could, if we needed to have a new entry on our list between sequence 10 or like line 10 and line 20, we could just add it in as line 12 or 13 or 14. We have a few options there. So that's handy too. All right, so we are in access list configuration mode, and we want to say deny. And we could say host name. So we could, well, that's if you have name resolution. If you use a host name, you have to resolve it to an IP address. So we can specify an IP address to match here. We could use the keyword any, or if we want to do an exact 32-bit address, we could use the keyword host, and it would just match on the exact 32-bit address. But in our case, we want to match on 10.16.0.0/21. And forgive me a cruel chuckle, but that syntax is not going to fly because that's what we want to do. But in order to tell this access control entry that we want to deny the 10.16.0.0/21 address space, we have to put wildcard bits in. So we are going to have to calculate what would be the wildcard bits to say we care only about the first 21 bits for matching, and we don't care about the other 11 bits. Yeah, I think that's it. Yeah, we don't care about the remainder 11 bits. Let me walk you through that. And again, if you haven't been through our CCNA, our Subnet Saturday series yet, which is in progress, please feel free to join us. There's a playlist just for that to get caught up to speed just on IP version 4 and how that works. So let me, I'm going to clear off my screen here, and let's go ahead and let's do some math. Our goal, should we choose to accept it, is to find out what the wildcard mask is that says we don't care about matching. That's an E. We don't care about matching on last 11 bits. All right, so here's what I would do if I was asked to calculate this. Now, the reality is that people who work in the field a lot, you're going to have the opportunity to become very familiar as you work with IP addresses over and over and over, just to see it and say, oh, I know what that is. I was always amazed. I remember one of the first really guru mentors I worked with when I first got into networking. Well, when I first got into networking, it was IPX. IP wasn't even a thing on local area networks back in the 80s. But when I first started working with IP, I remember looking at some guys that was like, amazing. Just in their head, they're like, boom, boom, boom. Oh, that's that. And I thought, wow, that's amazing. I wonder if I'll ever get that good. And the answer is nope. I'm not that good yet. No, but in all seriousness, the more you work with IPs and subnets, the more you'll be able to visualize or process those in your mind without actually doing the math. But I'm going to walk you through the math so you know exactly how to pull it off. So this network 1016, we know we want to match on the first 16 bits. So if we were going to draw out our powers of 2, which is a great idea almost always when working with this kind of thing, 1, 2, 4, 8, 16, 32, 64, 128. 1, 2, 4, 8, 16. Great. So these are the powers of 2. And I'm just going to put a period here. And we know that the first 2 octets, 10, 16, we want to match on. And so we know the wildcard mask or the wildcard bits for those 2 octets are going to be 0.0, which means we want to match on the 10, we want to match on the 16. However, it's this third octet, which I will put in a slightly different color here. It's this third octet that we're focusing on right here. So we'll imagine this the third octet. So second octet over there, third octet here. And let's just do the mask in visual representation. It would go something like this. If the mask is 21 bits, we would say, well, it's 16 bits up to this point, right? Because we have the first 8 in the mask and the second 8 in the mask, 16, and we're going for 21, so it would go like this. 17, 18, 19, 20, 21, stop. Draw a line between the network over here and the host over here as far as the network is concerned, and these would be zeros. So the mask for that third octet in a /21, the decimal mask would be 255, the normal mask, 255 dot, and then whatever the sum of these is, 128 plus 64 plus 32 plus 16 plus 8, let me do the fast math there, 248. And that's one of those values that after you work with it for a few weeks or months, you can either mathematically add them up or not, either way, or just know it. And then it'd be 0. So that's the mask. And the wildcard bits would be the inverse of that. Here's how I remember that. If the mask is this, the wildcard mask, see this right here, how it's the W? It's like mirrored. It's like a gift. It's like you take the mask, the M, you flip it upside down, you invert it, and that becomes the wildcard bits that we're going to use for identifying all the host bits that we don't care about matching. So it looks something like this. So it'd be 0 here in the wildcard mask, meaning we care about matching on the 10. It'd be a 0 here in the wildcard. And actually, I got to come clean on this. In network statements for OSPF, it literally is a wildcard mask. And when we think of the word mask, they have to be contiguous. Like the bits in a normal mask are on until they're off, and then they're all off. And in a wildcard mask, the bits are all off, meaning we want to match those portions. And then when they turn on, they stay on. That's a mask. So whenever you hear the concept of a mask, think of contiguous bits, either ones or zeros, until they stop and then it flips and they stay the same. Maybe it's too early in your journey of Cisco, but I want you to know up front that in an access control list, the bits don't have to be contiguous. So you could actually identify, I want that bit to match. I don't want that bit to match. I don't want that bit to match. And they don't have to be contiguous. So that is beyond the scope of what you're required to implement as far as CCNA. But once you get into CCNP and certainly CCIE, that is going to be a thing that you need to be aware of. So for now, just realize that in OSPF network statements, wildcard masks are contiguous. And as far as we care now for access control lists, the wildcard bits, we're also going to do them contiguous, meaning once they flip from ones to zeros or zeros to ones, they're not going to change back. All right. Glad I got that off my chest. All right, so here we go. Now for this third octet, if we flipped all these, if we're looking for the wildcard bits, we would say 0, 0, 0, 0. It's the inverse, and 1, 1, 1. So this is the mask of 248, and this is the wildcard mask of 7. And another way of doing this is you could identify this least significant bit that's on in the network mask, which is 8, and subtract 1, and that would also get you there. Or you could take 255 for the value of an octet minus the mask, which is 248, and that would get you there. So any way you want to slice it, there's 3 options there that I shared with you about how to do that. And if you need a little more background on that, please visit me in the OSPF wildcard masks video where we talk about that in quite a bunch more detail. So getting back to this wildcard mask, we would have a wildcard mask of 7 because we don't care about the last 3 bits of that third octet, and the last octet would be 255 because we don't care about any of those last bits as far as matching. So what this would mean is, let me go ahead and use a different color. Let's use black. This statement right here would be deny 10.16.00 followed by a space, and then we'd put the wildcard mask of 0.0.7.255. And what that means in measurable terms is that we want to match on the first 21 bits, and we don't care about the remainder 11 bits. All right, that's fun to do. That is not something that a brand new person, first time they've ever seen IP, is going to say, "Yo, I totally understand that." But but I would encourage you to go through the playlist of Subnet Saturdays. It's got like 4 or 5, or, going on 6 videos, I believe now. And we're just going to build on that step by step by step. So you can actually look at this, and even without doing any of the binary, after some practice, you can say, oh yeah, the wildcard mask for that is going to be, the block size is 8, got it, and -1 is 7. That's the wildcard mask for that octet, and then the remainder is going to be 255. All right, so let's implement this. Now that we've talked about it, let's go ahead and implement it. So I will back off that /21, and we'll specify wildcard bits. Notice it doesn't say wildcard mask, it just says wildcard bits. So we'll go ahead and say we care about matching on the 10, we care about matching on the 16, and we care about matching on the first 5 bits of that third octet, which is a 0 here. So those first 5 bits have to be 0. And then we don't care about the last 3 bits in that third octet, and we don't care about the last octet at all. And then we are going to add the keyword log, which is going to generate some log messages for us when and if that access control entry is hit. And that's handy for troubleshooting and so forth. Now, another interesting note about the log option here is that there could be like 11 billion packets coursing through our networks, right? Like, just going. And if we had log messages generating console messages for all of those, that would be unmanageable. So what Cisco does automatically, no extra charge in the background, is that when there's a match on the access control list for a certain packet flow, it'll generate a console message, it'll put it in the log file, and then it's going to peace out for 5 minutes. And it's just going to say, yeah, I told them 5 minutes ago, and I'll just relax. And it could still be happening in the background. And then the Cisco router says, you know what, in 5 minutes, I'm going to go ahead and give them a summary and say, over the last 5 minutes, this happened, 2,000 times or 1,000,000 times or whatever it is. And that way, we're not going to get flooded with console messages every time there's an access control list that's matched, whether it's in NAT or whether it's in filtering, which we're about to do, or if it's used for quality of service. Okay, so that's our access control list. Now, what is the problem with this ACL? The problem is twofold, really. One, it's just sitting here in the config. It's not applied to the interface. And secondly, there's no permit. So if we went to this router right here and we applied that access control list, and we said, dear Mr. Router, on this interface, gig 00, think of that like the door. Like that's the door to the party that you and I were standing at. And if we tell this router, hey, here's your list, check everybody before they come in and make sure they are permitted. And if they're not permitted, there's an implicit deny. So that access control list that we've written so far with one entry, with one line, with only a deny, is going to deny all traffic inbound because nothing's being permitted. Let's solve that by adding on a permit statement at the end of that access control list. So we'll go back to our interface and let's do it. This is how we would add that. Permit any. And because we're only matching on source, that basically means any source IP version 4 packet. There's separate sets of access lists for IP version 6. So for IP version 4, that would do it. And we can verify this with the do show IP access list. And because I'm not in privilege mode, I've got to type some of that out, so that should do it. So let's just show IP access list, and it's saying we have a standard access list named sorry AZ, that sequence number 10, think of it like line number 10, simply says deny 1016.00, which means the first 21 bits of that have to match. And if they do, deny it. And then if it doesn't match that line 10, then the access control list, once it's applied, will look at line 20 and permit everything else. So the next step is to go ahead and apply this. And we are going to apply this on this interface, gig 00, on this router. And that brings me up to another decision point. When we apply this access control list, we can apply it in one of two directions. We can apply it inbound. And here's what literally inbound means. Because it wasn't straightforward. I remember a lot of people in my career of learning Cisco and working with Cisco that got a little bit confused about inbound or ingress. And so I just want to make sure it's clear. If we tell this router to take that access control list and apply it inbound, that is from this router's perspective. So when this router is sitting there having a good time and a packet is coming into its interface from the outside world, coming in, that is referred to as ingress or inbound. And that we can tell the router to pay attention to any inbound traffic based on the access control list and then filter with the permits and the denies based on that list. The other option, besides in, is out. So if we wanted to, I'll go ahead and clear the screen. If we wanted to, we could create an access control list that filters certain traffic and we could apply it out. But in this case, we wouldn't find too much traffic being sourced from 1016.0 trying to go out here. But what we could do is we could apply that same access control list outbound on gig 10 or gig 20. And if that's the only two other interfaces, that would also work. So this would be an example of applying that same access control list outbound on these two interfaces or inbound on this interface. And so from a perspective of functionality and a perspective of, effectiveness, it makes more sense in this topology to apply it inbound on gig 00 because it's closer to the traffic. And if we had it on the outbound interfaces as outbound, then the router would have to get the packets, do a route lookup, make a decision, start to forward it in its mind, and then say, oh, access control list, and kill it. So we're saving some processing on the router also by having it closer to where the customer's traffic is coming in from. All right, so let's apply it inbound. I'll go ahead and just confirm that here. So we're going to apply that access control list inbound on R1. And also, this is so important. Before we do that, we should probably verify we have network connectivity through that router. So let's do a show IP interface brief. So gig 00 is 10.16.6.5. I just want to make sure that the client, Bob's computer, is actually going through that interface. So we can verify that by going to Bob's computer. And as we often do in these live streams, I'm going to verify the IP address on this device. So on a Windows computer, be IP. It's like, why isn't this tabbing out for me? Well, PowerShell might. Anyway, so IP config on a Windows computer will show us the IP address here, 10.16.0.10, and let's do a trace. That's how you spell trace in Windows 10 speak. -D, don't bother doing name resolution, out to 192.168.1.100. And what I believe is that IP address lives out here on this pseudo internet off of R1. So if it works correctly, the packet should go something like this. It should go out of Bob's computer, down the switched network, routed by core 1, routed by R1, and then forwarded onto its destination. So this multi-layer switch is acting as a router. So is this one. And so PC 10, this PC has the default gateway of core 1 set. So the path should flow in this direction. As I look at this, regarding layer 2, the path from access layer switch to core 1, depending on how spanning tree is working, could go this way as well. But logically, from a layer 3 perspective, it's going to be routed from this PC to this router to this router to its destination. So let's go ahead and verify that. I'm excited. I hope it works. I really do. All right, so I'm going to click in this window, press enter. Oh, there we go. So the first hop is 10.16.0.1. That is the multi-layer switch, which is the default gateway. Great. There's 10. Okay. Yep. So there's router 1 in the path. I just want to make sure we're sending traffic through that path. Otherwise, the access control list isn't really going to be filtering too much of anything. So we'll go back to our admin machine. And here's how we apply an access control list. We go to the interface where we want to apply the access control list. So we want to go to interface gig 00. So we'll put that in. I just did a copy paste there to save typing. And then we'll do an IP access group. And I want to talk with you just for a moment about this command. Whether it's a standard ACL or an extended ACL, whether it's numbered or named, this is how you apply a group of access list statements that are in an access list to an interface for the purpose of filtering traffic. So when it's called, the command is IP access group, think of what we're about to do is take this access list, which is a group of lines, of entries, and we're going to apply them to this interface. So the syntax is IP access group, and then we use a question mark, and then it wants the access list name, which is right here. I'm going to copy and paste that so I don't have a typo. And then it wants to know, okay, do you want me, says the router, do you want me to enforce this access list inbound as traffic is trying to come into gig 00, or as traffic is trying to leave gig 00? And we want it to apply inbound. So any traffic coming from Arizona, as it goes down to router 1 and in on its gig 00 interface, that's where we want the access control to take effect. So we'll go back to our management computer and we'll use the keyword in, and we are done. So, oh, that's not good. Oh, that's not good. Look at that. Okay. Oh, wow. 10.16.0.10. That's Bob. Bob, what are you doing? So, oh, you know what? I think, hold on a second. Let's do ipconfig /all. 10.16.0.1, default gateway, DNS server. Okay, so here's what I think was happening. Bob has a DNS server. That's a server that is used to resolve names like cbtnuggets.com into an IP address. And he has a DNS server of 10.1.0.111. And so to reach that server, it's on his local network, he forwards it to his default gateway. And it's my belief that the default gateway, which is this guy right here, let's just do a show IP route. Oh, he doesn't have a default route. He doesn't have 10.1. I would have guessed that router 1 or core 1 had a default route, and that's why it was forwarding. Anyway, long story short, based on the packets we saw and the packets we had denied, there was some traffic being denied from Bob from this computer as it was trying to go through that interface on router 1. So that happened. That's real. The packets aren't lying. All right, so it denied 10.16.0.10. It denied, oh, and here's a couple more. Wow, this is fantabulous. So, oh, and then okay, there we go. There's the answer right there. This is fantastic stuff. I'll tell you why. It's because we are having an opportunity to see the devastating effect that an access control list can have by denying traffic that we didn't intend to deny. And here's what I'm talking about. So we've got core 1 and core 2, which are two multi-layer switches acting as routers. So I'm going to draw circles. And then we have R1, and they are all connected to the same network there. And I would, based on this, it's the 10.16.6 subnet. Anyway, and what's happening is R1, and I'll put it in red here, R1 has this access control list that says deny anything from 10.16.0.0/21. And we know the wildcard mask for that is 7.255. But it's got that there, and so it killed Bob's packet, which we're happy with. But what we aren't so happy with is we accidentally... I'm saying we accidentally, like it's your fault. No, I did it. I totally did this. I put the access list, control list on there. I wasn't paying attention to other control plane traffic, like routing protocols that are communicating with each other. And as a result, we killed some traffic that's required by OSPF. They couldn't form the adjacency. The hello messages stopped getting in. And as a result, core 1 and core 2, and they weren't seeing the hello messages, and as a result, they lost their neighborships. They weren't responding back and forth. So because we denied the traffic from Core 1 and Core 2 accidentally here, that's these two guys, we also lost our OSPF neighborships. So that is the router ID for Core 1, and that's the router ID for Core 2. Now, I want to give a shout out and a thank you for the person who recommended that we use named access control lists, because by doing so, it makes it really easy to add a couple of entries in our access control list to permit specifically the 10.16.2.2, or 10.16.2.1 and 10.16.2.2, which are the IP addresses of Core 1 and Core 2 respectively. So let's fix this and bring our neighborships back up. With OSPF, we just lost our routing. Our routing is now thrashed. So just to demonstrate that as well, this is great. Let's go back to Core 1. We did a show IP route just a few moments ago on Core 1. Look at this. It now has a few routes that are local. Oh, that's just, yeah. It knows how to get to the loopback of Core 2, and Core 2 knows how to get to the loopback of Core 1, but that's it. All the other routes for all the rest of the network are dead because we lost our OSPF neighborships. So we'll fix it. All right, so we'll start with a show IP. We can either do a show IP access list, that works. But if you only have IP access list, you can just shortcut that a little bit with the show access list, and that'll show you all the access lists, but all we have is just this one, so it's not a big output. So let's go ahead and edit. We're going to add 2 permit statements above line 10. Because they're processed in order, we need to put the permit for Core 1 and Core 2 above the deny for the rest of that /21 10.16 network. So we'll do that. IP access list, extended, and it is, oh, look at that. It's standard. That would be a different access list. And then the name of that access list is this bad boy right here. And then we'll put in line number, how about line number 5? And then we'll go ahead and specify permit. And we want to permit 10.16. Let's take a look at who we killed. So it's 10.16.6.2 and 10.16.6.1. What we could do is we could go ahead and we could just allow 10.16.6 anything to come in as an exception, or we could be very granular. So it's totally up to us. So let's do 10.16.6. And that, by the way, is our 5-minute summary that just came up. So over the last 5 minutes, here's what I did. And every 5 minutes, it'll give us another summary of the denies. So let's do a 10.16.6. 6.1 with a wildcard mask of this. I'm just going to show you a few ways of doing it. And it says, you put 5 zeros there. Okay. So what this statement says, it says sequence number 5, line 5, is go ahead and permit the host 10.16.6.1, and the wildcard mask of all zeros means those bits, we want to match on them 100%. That's explicitly allowing just that one IP address to be permitted in the access control list. Another way we could have done that is this command. So for 10.16.6.2, we can use the keyword host and then let the other guy in. And this is effectively the same thing. Oh, thank you. It says you just put in 5. Didn't mean to do that. I want line 6. So if we do a show IP OSPF, oh my gosh, show IP, because we lost our adjacency. My brain's in OSPF mode. Do show access list. We don't have that many. So now we have this access list that is permitting the exact host of 10.16.6.1, and that's because we use this wildcard mask of all zeros right here. Then we have the permit of 10.16.16.2, and that's because we use the keyword of host. And the other shortcut is if we just put in permit, and I'll just add another one for fun, hit the up arrow key, and do a line 7 this time so I don't overwrite my other line. Permit, and we just put in the IP address of 10.16.6.3. We don't really have it that one we need to permit, but I'm going to do it anyway. And then we show the access list by using just the host, or just using the IP address itself without a mask. It assumes that you want a 32-bit match. So this was done with a wildcard bits of 0000. This was done with a keyword host, and this was done just by putting in the IP address without any wildcard bits specified, and it assumed that we wanted to match on all bits. Now, don't blame the messenger that there's 3 ways of doing the same exact thing, because that's what they are. They are the same exact results, and in a situation where you're taking certification, they could ask you this in any way. Like, what is the result of doing this? And if you know it, you can just answer it. Like, oh yeah, we're matching on all 32 bits because use the keyword host, or use the wildcard bits of 0000, or with the standard ACL, he just put in the IP address and pressed enter and assumed that it wanted a 32-bit match. Okay, so now that we have this in place, let's verify our neighbors came back. Show IP OSPF neighbors. Yeah, okay, so we have a neighborship with core 1 and with core 2. That's great. And if we do a show IP OSPF neighbor, that is neighbor, and we do a show IP OSPF interface, look at that. I'm repeating myself. All right. Oh my gosh. And let's do a brief. I want the brief version. So what this means right here on gig 00, see how it says DR OTH? A multi-access segment where we have a designated, so in OSPF, if we have a network type of broadcast or a network type of non-broadcast, in those 2 conditions, we're expecting to use a designated router. The first device on the network is going to be the DR. If 2 come up at the same time or more at the same exact time, they're going to duke it out, and the one with the highest priority is going to win. If the priority on the interfaces, which is 1 by default, is the same, then it's the device with the highest router ID is going to be the DR. And then the one that is in second place will become the backup designated router. And then all the other devices on that network segment will establish a full adjacency with the DR and the BDR. But what they won't do is they won't establish a full adjacency with any other routers on that segment that are not the DR or BDR. So the role for this device, because there's a DR and a BDR present, the role for this device is a DR other. Like, I'd rather not be a DR or a BDR. That's a fun way of remembering it, but that's what this role is. That's what the interface is. So originally he may have been a DR, but once he went down, and then the 2 other routers said, hey, we're going to do this. When he came back up, there was a DR, there was a BDR, and so he said, great, I'll be a DR other, and I will establish full adjacencies with both of you. And we can see that with the show IP OSPF neighbor. All right, so there's the full adjacency with the BDR, which is core switch 1, and there's the full adjacency with the designated router, which is core switch 2. And I assume core 2 won because it had the higher router ID. Although, we'd have to look at the states before it happened. Okay, so let's take a look at the interface. The question might come up, well, Keith, how do we know what IP or what access control lists are being used for filtering on an interface? And the answer is we'll just ask it. We'll go up to the router and say, hey, can you show me the IP information regarding gig 00? And it will show us if there's any access control lists applied on that interface for either inbound or outbound traffic filtering. So let's take a look. And here's what it would look like. Show IP OSPF. Oh my gosh, I have freaking OSPF on the brain. Show IP interface gig 0/0. And I'll tell you one of the reasons for that too is that I'm finishing up the encore portion at CBT Nuggets on OSPF, and so I've been doing these really amazing, super fun labs with OSPF and multi-areas and filtering and autonomous system boundary routers and all these cool things. Anyway, so what this is showing us is, and I will hit a key to stop there, it's saying right here that the inbound access list is sorry-AZ. And that's the filtering list it's using. And if you do a show access list, it will show us that we have this many matches on that line, that many matches on that line, no matches on that line because we don't have an IP address of 10.16.6.3 in our network. And then we have a deny for everything else, which means Bob should no longer be able to go ahead and send packets. Let's verify that. So Bob's up here. His traffic as it goes down through the router should now be, what's the word I'm looking for? Oh yeah, rejected. So let's do a trace. Same trace we did earlier. So it made it to router 1, and then router 5 said, yeah, I got your packet, and I killed it because of an access control list. And R1 was courteous enough to send an ICMP message back that said, yeah, I killed your packet. So here's the details of the packet that I killed, and good luck. You want to try it again? Do it. So if we tried it again, it wouldn't matter. He's killing all IP traffic. So in this set of videos, what we've done is, or what is this live stream, we've taken a look at the world of a standard access control list. And let me look at my notes to make sure I got everything I wanted to cover. Standard access control lists can be used for lots of things. And their major purpose is matching on traffic. And then how we apply them after we create them, that's going to depend on what functionality we want. In this case, we applied them to an interface, applied access controllers to an interface for the purpose of filtering. But we could also use it for NAT by specifying who can be translated for network address translation. We could also use it to identify what traffic we want to give priority in the network for quality of service and other features like that. All right, so a standard ACL. The number for a standard ACL is 1 to 9. 1 to 99. All right, that was difficult. So 1 to 99 is the standard access list range. If you're using numbered, if you're using names, you can just make up a name, and then when you create it, you specify that this named ACL, this NACL, is named Bubba, and it is a standard access list. And then you can add the entries to it. They are processed. The second thing I wanted to cover is they're processed from top to bottom, like a list. So as packets come in, the router looks at the first line, whatever that sequence number is. Maybe it's 10, maybe it's 5, maybe it's 6. But he looks at the first line. Is there a match? Nope. Next line, is there a match? Nope. Third line, is there a match? If there is, it's then going to permit or deny that traffic based on that specific third line that it matched. If traffic comes in that doesn't match any of the entries, the router says, yeah, you're not on the list. You're out. I'm going to deny you. And that's why it's called an implicit deny. And then the third thing I wanted to mention was that they are used for filtering. They can be used for filtering, which is what we just did a few moments ago by creating an access control list, applying it to an interface with the IP access-group command, and then we specify on the interface, should we be checking the list for traffic coming into the router, says the router, or going out of the router. And if you do that from the router's perspective, like his or her attitude, you'll always get the direction right. It's like, where should this go, in or out? It's like, well, what do you want to control? Do you want control traffic that's trying to go into that interface? From the router's perspective, it's in, no matter where that router is. That router could be deep in the heart of the company or out on the edge of the network, but that in concept is regarding the actual interface from the router's perspective. All right, so that's what I wanted to do. I'm going to stick around for a few minutes and do Q&A and answer some questions. I'm going to formally close the live stream, and then once it gets up there on YouTube, I will trim off the end. So basically, for the individuals who join me in the live stream, like you, the only people that get the benefit of that is going to be you. So I'm so grateful you're here. I'm going to go ahead and close off the live stream and then stick around and we'll do some Q&A. So thanks everybody and have a great rest of your day.
Do you ever feel you don't get out what you're putting in? All your hopes are never